Let us take a closer look at the speculative decoding algorithm. With the approximation model MQ, the target model MP, and the initial prompt called as the prefix as the inputs, we first take the prefix and the approximation model, and we run this for loop. Basically, we autoregressively generate gamma tokens, and at each step, we keep saving the output probability distribution in this variable Q. Okay, and after this, the code asks us to generate gamma number of context vectors and give all those context vectors to the target LLM MP in parallel and make it generate gamma number of p probability output distributions. So we have prefix plus the first token. Then we have prefix plus the first token plus the second token generated from the approximation LLM all the way until prefix plus the first token plus all the way until the gamma token. So you take the prefix, this is the first context vector, prefix appended with the first token generated from the approximation LLM. That's the second context vector, and so on and so forth. You have all these gamma context vectors. You give each of these to the target LLM. And when you do that, you're going to get an output probability distribution for each of those time steps. And you save all of that. So you have P1 of X, P2 of X, all the way until P gamma of X. And you're going to save all of them in these variables here. Okay. And this might look a little daunting to be able to run an LLM in parallel gamma number of times. But in modern transformer architectures, the way it plays out is that we concatenate the um, we concatenate the prefix with all the generated tokens from the approximation LLM. We concatenate all of these. We call the target LLM only once, and that is going to generate all the output probability distributions for these gamma time steps at once in parallel. That's mainly because of how transformer architectures are modeled. So you have P1 of X until 1. So you have P2 of X until 2. So you really are able to only get away with calling the target LLM only once while you have called the approximation LLM gamma number of times. Now that is the beauty of this, right? So um, if all the tokens get accepted, you would have generated gamma extra tokens per one LLM call, per one target LLM call. Now that's like a massive speed up there. We're going to see how much speed up is going to be exactly in numbers, or approximately in numbers soon. But that is really this part of the code here. Now, after this, right, you're now going to create those ratios, P of X over Q of X, run that random experiment, and either accept or reject tokens. So the way you're going to perform that random experiment of accepting or rejecting the token given by the approximation LLM using the probability output probability distributions is as follows. So for each time step, you denote um, a uniform random variable located, a uniform random variable. And you have these probability distributions, right? So you just created all of these. And so you're going to compare each of these. So you're going to sample gamma number of uniform random variables, one for each time step. And at each time step, you're going to compare the value of that particular random variable's value after you perform that experiment with this particular ratio here. Okay. So, and you keep doing that until at some location here, you have the first occurrence of the sampled value actually being greater than the probability distribution here, right? So, uh, so you have sampled R1 compared it with P1 over Q1. Maybe R1 was lesser than that, so you do nothing until at some point at um, in the sequence you have an nth index where the sample value was actually greater than this particular ratio here for that time step. And that you would call it as a rejection there, and you would note the index and call it n. So that is this part of the code here with all this fancy min and the set notation. Basically, we are trying to extract the first location where the sample value r is greater than the ratio of p of x over q of x for that particular time step. So we want the first time step where we have this r being greater than that ratio. Now, and we're calling that a rejection. Why is that? If you think about, now this might be known to many, but I'm just like putting this here in for completeness. So the way we are, what are we trying to do actually here? We would want to do a biased coin toss, right? And that biased coin toss should generate the first outcome with P over Q probability and the second outcome with 1 minus P over Q probability, right? So if we think of a uniform random variable and we define a value z that lies in between it, the probability that when you sample a value, it lies here in this region. So p of u less than or equal to z is actually equal to z itself. This is the CDF of the uniform distribution. This basically implies p that u greater than z is actually equal to 1 minus z, right? So you perform, and when you make z equals p of x over q of x, you can immediately see that the probability that z lies here, I mean the sample uniform value lies here, the probability of that is equal to 1 minus p of x by q of x. So when we are saying that check for r being greater than this ratio, the probability that that happens is actually the rejection probability that we want. And that is the case where we reject things. So that is the first index where we have rejected something. Also note here that p of x over q of x is going to lie between 0 and 1 only when p of x is less than q of x, right? That is when the target LLM does not think that the approximation LLM's predicted token is as likely. In the cases when p is greater than or equal to q, then this value would have lied somewhere outside. So this is p of x by q of x when p is greater than or equal to q, right? So in that case, the probability that r is greater than p of x over q of x, so r is going to be somewhere here. So the probability that this happens is 0. So you'll never see that. So in cases of acceptance, you're not going to satisfy this condition here. But in cases when the target LLM does not think that the approximation LLM's prediction is as likely, you're performing a random experiment with two outcomes and with the requisite probabilities. And the first occurrence of the outcome is what we are interested in. And we are denoting that as a rejection and calling that index as n, right? I hope that part was clear. And so once we have this first rejected index n, we are going to throw away all the tokens um, from n to gamma, right? So once we have hit a rejection, we no longer accept tokens from the approximation LLM. We accept it until then, but after that we don't. So we initialize the p prime of x distribution with the next time step distribution of mp, right? So if you remember, we have generated, we have run this for gamma number of time steps. So we also have like an n plus 1th time step distribution here, right? So we initialize it to that. And if n is less than gamma, that basically means we had a rejection. That is when we bring in this new normalized probability distribution and sample from it. Otherwise, we sample from the gamma plus 1th time steps probability distribution that was produced when we ran all these gamma tokens in parallel earlier. So what we essentially are doing is we are first generating few tokens from the model autoregressively, from the approximation model autoregressively. We are taking all those tokens, concatenating them with the prefix, and giving them to MP once. MP is going to give us all the gamma output probability distributions, uh, and then we are going to use those P and Q probability distributions, run a random experiment using uniform random variables, and get the first index where we hit a rejection. And if that index happens to be less than gamma, that basically means that we have had a rejection somewhere in the middle. We are going to only accept tokens up until then, sample a new token from this new normalized distribution. And we are only going to return the accepted tokens and this new token that was generated either from sampling from this normal distribution, or in the case when all the tokens are accepted, you simply sample from the gamma plus one. You simply sample from the gamma plus one uh, time steps distribution that MP has produced, and that's your last token. I hope the speculative decoding algorithm is clearer, both in terms of the pseudocode and in terms of how we may implement this in code. Thank you.